Have you ever seen that earthquake footage? You know, the kind where one building just completely collapses, pancaking down into a pile of rubble, but the building right next to it is still standing, almost untouched? It's wild. And you have to wonder, how does that happen? Well, it's not random, and it often points to a really dangerous, hidden flaw in how some of our buildings are designed. So let's get into it.
Right? It's a terrifying puzzle. One building stands, one is gone. This isn't just a matter of luck or chance. It's actually more like a structural detective story. And in so many of these cases, the clues all point to this one hidden vulnerability, a flaw buried deep in the building's very bones that turns its design into its own worst enemy. And here it is. This is our prime suspect. It's called the soft story. Now, that's a term you probably haven't heard before, but trust me, it's the culprit behind some of the most dramatic and, frankly, preventable building collapses we've ever seen.
Okay, so to really get how a soft story can be so destructive, we got to look at the physics behind it. And honestly, the best way to wrap your head around it is to just think about your own body, specifically your knees.
Think about it. If you were to jump off, say, a small ledge, what do you do when you land? You bend your knees, right? Of course. Your body does it instinctively. That absorbs the impact and distributes the force safely. But what if you landed with your knees totally locked and rigid? Oh, it's painful to even think about. All of that force would slam directly into your knee joints and they would just snap. That's a brittle failure. A soft story in a building is exactly like that weak, locked knee. So here's the official industry standard definition. A floor is considered soft when its ability to resist side-to-side forces, what engineers call lateral stiffness, is less than 70% of the floor right on top of it. It's not a gradual change. It's a sudden, jarring drop in strength that creates that one disastrously weak point.
And I guarantee you've seen these buildings everywhere. You know those apartment complexes with a big, open-air parking garage on the ground level? Or maybe a sleek office building with a huge, glassy two-story lobby? Those wide open spaces are way more flexible than the heavy, solid, boxy floors stacked right on top of them. That is the classic soft story setup.
And this is the terrifying result. Look at this number. In a properly designed building, when an earthquake hits, the whole structure sways together, with each floor drifting maybe 1%. But in a building with a soft story, all that violent energy gets funneled into that one weak floor. It can drift a catastrophic 5 or even 6%, while the floors above it barely move. That incredible strain is what snaps the columns and causes the whole building to just pancake down on itself.
Now, I know what you're thinking. Don't we have, incredibly powerful computer software to catch this stuff? And yes, we do. But here's the crazy twist in our story. Sometimes, the very tools that are supposed to keep us safe can end up hiding the danger in plain sight. It all really comes down to this classic timeless saying in the world of computing and engineering: garbage in, garbage out. You can have the most sophisticated software on the planet, but it's completely useless if the information you feed into it, the basic assumptions, are wrong from the start.
And this leads to something called the black box paradox. An engineer opens up the software and gets this amazing God's eye view of the entire building. They can see every single beam, column, and connection. It gives you this feeling of total knowledge and control. But here's the trap. If they just trust the software's default settings without questioning them, that powerful model can create a deadly and completely false sense of security.
So what's actually going wrong here? Well, a key problem is that the default computer model is often just the skeleton of the building, just the columns and beams. It totally ignores other stuff that adds stiffness in the real world, like interior partition walls or staircases. This makes the computer model artificially flexible. And because of the physics involved, that extra flexibility tricks the model into dangerously underestimating the real forces an earthquake would throw at it. So how do engineers fix this? Thankfully, there's a critical safety net built into the process. It's called scaling. First, they do a simplified, old-school calculation to figure out the absolute bare minimum force the building code requires it to handle. That's the static force. Then they run their fancy computer model to get a more precise number, the dynamic force. And here's the rule. If the computer's number is lower than the code's minimum, which, happens a lot, they have to manually scale up all the forces in their model until they match that safe baseline. But just trusting that process isn't enough. A really good engineer has to act like a forensic detective. They have to run an audit on their own work, on their own model, to hunt for any hidden flaws. And they use a specific 4-point checklist to do it. Okay, check number 1 is called mass participation.
Basically, the software analyzes how the building is likely to shake. The rule is simple. You have to make sure your analysis accounts for at least 90% of the building's total real-world weight. If you don't, you might only be analyzing, say, 60% of the mass. That's like designing a building that's 40% lighter than it's actually going to be. And that's a recipe for absolute disaster.
Check number 2 is for something called the P-delta effect. This is a sneaky secondary effect. See, as the building starts to lean over during an earthquake, its own weight, gravity, starts to pull it over even more, trying to topple it. This table shows the safety thresholds. If the P-delta value is under 0.1, you're good. If it's between 0.1 and 0.3, that's a warning sign, and you need to beef up your design. But if it's over 0.3, whoa, stop everything. The building is fundamentally unstable and has to be redesigned from the ground up.
Now, the third check is my favorite. It's beautifully simple. It's just the eye test. You literally sit down and watch an animation of your computer model shaking. And you ask yourself, does this look right? Do you see completely bizarre, impossible things happening, like a balcony that detaches and just starts flying through space? If it looks physically wrong, guess what? It is wrong. Your model is broken, and you have to go back and fix it. So before we get to the final check, you have to see this. According to actual engineering audits that review these designs, the last step we're about to cover is the single most common reason that structural models get rejected. This is the one that people mess up all the time. And that final step is the RSA Scaling Verification. This is it. This is the critical moment where the engineer has to double-check their own work and prove it. They have to show, with hard evidence, that they actually performed that scaling process we talked about earlier. They have to confirm that their too flexible computer model has been properly corrected to meet the absolute minimum safety standards required by law.
So all of this really brings us to a final, pretty sobering thought. Designing a safe building isn't just about getting the math right. It's about diligence. It's about being skeptical of your own tools and having an obsessive commitment to checking the work. And it really makes you wonder, doesn't it? The office, the school, or the home you're sitting in right now, how well was its model checked?